Hello friends, after a long wait, we are coming with a series of lectures on differential equations. Differential equations are essential for a mathematical description of nature, many of the general laws of nature in physics, chemistry, biology, economics, and engineering, and so many things. Differential equation allows us to study all kinds of evolutionary process with the properties of determinacy, finite dimensionality, as well as differentiability. So we know the basics of limit, continuity, and differentiability. So after that, the study of differential began very soon from the development of differential and integral calculus by Newton and Leibniz. In the year 1671, Isaac Newton first laid the foundation stone for the study of differential equation. So he is the father figure of this branch differential equation. And after that, the second man Leibniz introduced the term differential equation in the year 1676 to denote the relationship between differential coefficients, that is dx dy, with the real variables x and y. So this is the main history of differential equation. So in every natural situation we can find any differential equation. For example, fundamental law of motion in mechanics known as Newton's second law is also an example of differential equation which describes the state of a system. So motion of a particle of mass m moving along a straight line under the influence of specified external force F is also described by the following differential equation, that is mx double prime equals to F, where F is dependent on x, t, as well as the differential of the variable x, where x prime is the first derivative with respect to time and x double prime is the second derivative with respect to time. Differential equation is such equation which contains the differential coefficients of a function, but it may not contain the real variable x or y. For example, we can consider two equations, x dy dx equals to 5y as well as d2y dx2 equals to 3 dy dx. In the second case, that equation does not contain any real variable x or y, but in that equation differential coefficient is present. So what is the order of a differential equation? Order of a differential equation is the highest order of the differential coefficient present in that equation. For example, first order equation example is y2 dy dx square minus x dy dx equals to x square. So in that case, the highest order derivative is simply dy dx. So there is no second derivative. So this is the first order differential equation. And in the second equation, we can find d2y dx2 whole square equals to x square times dy dx whole cube. So in that case, there is second derivative. That means d2y dx2 term is present in this equation. So this is an example of second order differential equation. So this is the idea of order. So what is the idea of degree of a differential equation? Degree is the power of highest order differential coefficient. That means in the first equation, the power of highest order differential is simply 2. So that is, so degree of the first equation is 2, and in the second equation power of highest order derivative is simply 2. So in that case also degree is 2. So this is the main idea of order and degree of a differential equation. There are two types of differential equation. First one is ordinary and second one is partial differential equation. In case of ordinary differential equation, there is simply one independent variable and we have to consider the differential coefficient of the differential of the dependent variable with respect to the independent one. So for example, d2y dx2 minus 3 dy dx plus 5y equals to 0 is an example of ODE. But in case of partial differential equation, we have to consider partial derivatives of two dependent variables with respect to the independent. Or in other words, suppose z is the single variable and we have to consider two partial derivatives zx del z del x and del z del y. So xp minus yq equals to 3z is an example of a PDE. So an ordinary differential equation of first order and first degree is of the form dy dx equals to f of xy. That means the derivative will be a function of x and y. Or simply it will be of the form m dx plus n dy equals to 0, where m and n are the functions of x and y. For example, ex sin y dx plus ex plus 1 cos y dy equals to 0 is an example of ODE of first order and first degree. But an first order ODE of the form m dx plus n dy equals to 0 will be called exact if there exists a function uxy, so that we can write m dx plus n dy as du. That means the given equation can be written as the differential form. So in that case the equation will be called exact equation. Now one may ask that what's the necessary and sufficient condition of exactness of a differential equation. So a differential equation of the form m dx plus n dy equals to 0 will be exact if and only if the following condition will be true, that is del m del y equals to the del n del x. So this is the necessary and sufficient condition. But if any case, how can we solve a exact differential equation? Suppose this condition holds good, then how can we solve a differential equation? So in that case we have to consider integration m dx plus integration n dy, but in case of m we have to treat y variable as constant, and in case of n we have to consider simply those terms which does not contain x. So this is the main idea of solution. So for example, there is a problem, we have to check the exactness of this equation and then solve. So clearly we can compute del m del y and del n del x, both are equal, so this equation is exact, and the solution will be simply integration of 3y times x square minus 1 dx plus integration 8y dy. So that means in case of n there is no term which does not contain x, and in the right side that will be constant. So clearly we can find the solution of this equation. And next point is integrating factor. What is integrating factor? Integrating factor is such suitable factor multiplying by which a non-exact equation can be made exact. So for example, x dy minus y dx equals to 0 is an example of non-exact equation. But if we multiply this equation by 1 by x square, so in that case it will be of the form x dy minus y dx by x square equals to 0. That means we have d of y by x equals to 0. That means y by x equals to constant. So multiplying by 1 by x square as integrating factor, we can find a non-exact equation into a exact form. So this is the main idea of integrating factor. Obviously, the existence of one integrating factor implies the existence of infinitely many integrating factors of a differential equation. But the next point is what are the basic rules to find integrating factor. So first one is that suppose we are computing del m del y minus del n del x by n. That means in case of non-exact equation we are trying to find integrating factor. So if the first fraction is simply fx, that is only function of x, in that case e to the power integration fx dx will be an integrating factor. In case of second expression, if that fraction will be simply function of y, that is phi y, then the integrating factor will be e to the power minus integration phi y dy. For the third point, suppose m and n are both homogeneous functions of x and y of same degree. and the expression mx plus ny is non-zero. In that case, integrating factor will be the reciprocal of mx plus ny. And in the fourth case, suppose the equation is of the form y times f of xy dx plus x times g of xy dy equals to 0. In that case, integrating factor will be reciprocal of mx minus ny, provided that the denominator is non-zero. So these are basic rules to find integrating factors. Suppose we are considering a problem x4 plus y4 dx minus xy cube dy equals to 0. Clearly, this equation is non-exact because del m del y and del n del x are not equal. So in that case, we have to find integrating factor. Clearly, we can check that mx plus ny, this expression is simply x to the power 5, that is a non-zero term. So clearly the reciprocal of this term, that is 1 by x to the power 5, will be an integrating factor. So multiplying the whole equation by this integrating factor, we have 1 by x plus y4 by x5 dx minus y cube by x to the power 4 dy equals to 0. But in case of solution, we have to consider simply first portion, because in case of n, there is no term which does not contain x, because in case of n terms there is y by x to the power 4. So we can't consider those terms for the solution. So the solution will be given by integration of 1 by x plus y to the power 4 by x to the power 5 dx equals to constant. So we can easily find the solution. And the next point is the idea of linear equation. What is linear equation? Suppose we are considering a equation dy dx plus py equals to q, where p and q are some function of x or anything constant. So using e to the power integration p dx as integrating factor, we can write this equation as d dx of y times e to the power integration p dx equals to q times e to the power integration p dx. That means after integration we can have y times e to the power integration p dx equals to integration q into u to the power integration p dx plus some constant, and clearly we can find the expression of y. So this is the required solution of any first order linear equation. Suppose we are considering a equation x plus y plus 1 into dy dx equals to 1. So we have to check whether it is a linear equation or not, and then we have to solve it. So after rewriting this, we can have dx dy minus x equals to y plus 1. Then clearly it will be a linear equation in x, and integrating factor will be e to the power integration minus 1 into dy, because the coefficient is simply minus 1. So integrating factor will be e to the power minus y, and then multiplying by it we can have dy of x times e to the power y equals to something. Then after integration we can find the solution as x e to the power minus y equals to integration of y plus 1 times e to the power minus y dy, and easily we can find the solution of this equation, of this linear equation. But is any other form of linear equation? Suppose we are considering Bernoulli's equation. So common difference is that suppose we are considering an equation of the form dy dx plus py equals to q times y to the power n, where n is any integer. Then dividing both sides by y to the power n, we can have y to the power minus n dy dx plus p times y to the power y minus n equals to q. That means in the right hand side there is no term involving dependent variable, that is there is no term of y. So in that situation we have to consider the term of y, that is y to the power y minus n, as z. So let us consider y to the power y minus n as z. Then after differentiation and after substitution we can rewrite as 1 by y minus n dz dx plus pz equals to q, or simplifying it, we can write dz dx plus y minus n pz equals to y minus n q. That means in the right hand side there is no dependent variable. So from the given equation we have chosen a substitution, and after that we can solve this equation. So this is the idea of Bernoulli's equation. In the next slide we will solve a problem on. So this is the problem in which we have to use the idea of Bernoulli's equation. So given equation can be rewritten as dy dx minus y equals to 2xy square by e to the power x. That means after simplification of the given equation. So clearly in the right hand side there is y square term. So we have to divide whole equation by y square, and after that we will get 1 by y square dy dx minus 1 by y equals to 2x by e to the power x. So in the right hand side there is simply independent variable, there is no sign of dependent variable. So in that situation we have to consider the second term, that is minus simply 1 by y as z. So using this substitution we can have dz dx plus z equals to minus 2x by e to the power x. So after simplification we can write d dx of z e to the power x equals to minus 2x, and after integration we can write z e to the power x equals to minus x square plus constant, and finally e to the power x will be y times c minus x square. So this is the solution of the given Bernoulli's equation.